plate tectonics. So this is the chapter which is very important for the next chapter in earthquakes. So yes. In the last class, we have studied some portion about the plate tectonics, the scenery, what the scenery is, and how the plate moves globally. And now we are going to continue the study. And okay, let's start. And yeah, now here I will further introduce the types of faults and the earthquakes. Here, the three types listed below, and they are divided into such three types. The first one is strike slip faults, and which have already talked about, and so now we can review it. And the strike slip faults are vertical or near vertical fracture surface at plate boundary. They are also known as transform faults. And the motion of this kind of faults is entirely horizontal. And secondly, the thrust faults are fracture surfaces that dip at an angle between the horizontal and the vertical. The convergent motion within a volume of rock often generates such a fault, and the motion is partly horizontal and partly vertical. And the last type is the normal fault, and it is a fracture surface that also dip, and which is usually occur in divergent motion with and between bodies of rock. And such motion is partly horizontal and partly vertical, but opposite to the motion on a thrust fault. You remember the thrust fault, it belongs to the type of reverse fault. And when the reverse fault, the deep angle of this reverse fault is less than 30 degrees, we call it thrust fault. And now we are going to detailed talk about the three types. And the type one is the divergent margin, and is the where two plates spread apart at a divergent boundary. The hot sphere rises to fill the gap, and as it ascends, the rock experiences a decrease in pressure and partially melts. And the molten rock is called magma, which we have learned it on the first section, igneous rock. And the mid-ocean ridges occur in oceanic crust. They were found in every ocean of the world, and they form a continuous chain that circles the globe. And the oceanic crust is about 8 kilometers thick, which I mentioned in the last class. And here I use the birth of the Atlantic Ocean to show such a process. And the Atlantic Ocean, currently the ocean with the slowest production of new crust, is spreading at 2 centimeters per year, which is measured as the total separation on both plates. And it is spreading at 2 centimeter per year in the south of Iceland, from the south of Iceland in Europe, and 4.5 centimeter per year at the point of maximum spreading in the southern Atlantic. And when a spreading center splits continental crust, a great rift will form, and such as the Africa Rift Valley. As the two pieces of the continental crust spread apart, and the lithosphere will become thinner, and the underlying asthenosphere will rise, and the volcanism will start up and on Earth, and the rift widens and deepens, eventually dropping below the sea level, and then the sea enters to form a long, narrow water body like the Red Sea, which I have introduced in the last class. And the Atlantic Ocean did not exist until 250 million years ago, and the continents that now border it were joined into a single vast continent that Alfred Wegener named Pangaea. And about 200 million years ago, new spreading centers split the huge continent. And now, in the current time, the Atlantic continues to widen today at a much slower velocity, which is 2 to 4 centimeter per year. And next let's move to the characteristics of spreading centers. The earthquakes. The feature of earthquakes at the mid-ocean ridges occurs only in the first 10 kilometers beneath the seafloor and tend to be small. And the normal faults form parallel lines along the rifted margin. And the volcanic activity occurs at the mid-ocean ridges and continental rifts along the narrow parallel fissures. And the mid-ocean ridges rise 2 kilometers or more above the surrounding seafloor. And these are the characteristics of the spreading centers. You remember what is spreading centers? It's another name of the divergent margin. Yeah, you can check the slides in the PowerPoint. We have a nerd in the last class. And this figure shows the seafloor age, and the principle of isostasy implies the lower density rock rises to form a higher elevation. And the seafloor around the mid-ocean ridge for nearly all oceanic lithosphere is younger than 17 million years. And if the spreading rate is fast, a larger amount of young warm oceanic lithosphere will be produced. And also the range will be wider. And a slow spreading range will be narrower. And the Atlantic Ocean spreads slowly, growing wider at, I have mentioned 2 to 4 centimeters per year. And the Pacific spreading center is faster by the comparison, which is 6 to 20 centimeters per year. And the seawater circulates through cracks beneath the ocean floor, and the cold water percolates through these cracks, warms in contact with the subsurface rock, and rises convectively to form undersea hot springs. The seawater reacts chemically with lithospheric rock, reaching many mechanic elements form it, and a small fraction of the seawater remains in the rock, chemically bound within hydrous minerals like serpentine and clays. And about the carbon dioxide connection, as the oceanic lithosphere ages, it accumulates a thick layer of sediments such as clay and calcium carbonate from the shells and the internal skeletons of countless marine organisms. And the formation of calcium carbonate consumes carbon dioxide that is dissolved in seawater. And the seafloor sediments removed carbon dioxide from the atmosphere and thus have a long-term influence on the greenhouse effect and Earth's climate. So this is the interaction relationship between the carbon dioxide and the oceanic lithosphere, which is very important in our current climate of the Earth. Okay, next is for the type 2 of the fault, the convergent margin, which has another name of the subduction zone. And over 70 million years, the oceanic lithosphere can drift 1,500 to 3,100 kilometers from the spreading center. And as the plate cools, the density of it will increase. And the principle of isostacy demands that the plate subside as it grows denser. And the process by which lithosphere sinks into the external sphere is called subduction. And the margins along which plates are subducted are called subduction zones, and these are active continental margins of the world. And among the types of the fault, and the sinking snap warms, softens, and exchanges material with the surrounding metal. And under elevated temperature and pressure, the crust expels a number of chemical compounds, including water, carbon dioxide, sulfur compounds, and a small addition of this volatile substances can lower the melting point of rock by several hundred degrees of Celsius. And the hot metal rock immediately above the sinking snap starts to melt, and the magma rises to the surface to form volcanoes, and the subduction zones are marked by an arc of volcanoes parallel to the edge of the plate, like arc of volcanoes surrounding the Pacific oceans, which is called the fire ring of the Pacific, which has a lot of volcanoes and seismic events. And the carbon dioxide connected with this again, and the water, carbon dioxide, and sulfuric gases like sulfur dioxide and hydrogen sulfide return to the atmosphere. And subduction zone volcanic activity raises the carbon dioxide level in the atmosphere, exerting a strong influence on the greenhouse effect and Earth's climate. And the volcanism volcanism tends to replace the carbon dioxide that is lost from the atmosphere into the ocean and stored in the seafloor. The warmer or cooler episodes in past climates can be deduced from the fossils of ancient plants and animals. But as far as I know, some other scientists revealed that there's no strong proofs that suggest the carbon dioxide will intensely affected our climate. This is still convictions in the scientific issues. And the volcanoes frequently are formed at subduction zones. And at plate boundary, the plunging plate draws the seafloor down into an ocean trench, often 10 kilometers deep or more. And if the overriding plate is oceanic mesosphere, volcanoes form a series of islands called volcanic island arc, like Marina Islands or Alatia Islands. And if the overriding plate is continental mesosphere, a continental volcanic arc forms, and while sediment washed from the continent tends to fill the offshore trench, like Cascade Range of the Pacific Northwest. And another example is the Andes of the South, Andes Mountain of the South America. And the chemical analysis of subduction arc rocks disclosed unusual concentrations of rare elements, such as boron, and best explained by the expulsion of water and other volatile substances from the descending slab. And on the other hand, most subduction arc volcanoes occur roughly where earthquakes indicate that the top of the slab is 100 kilometers deep. And later I can share with you a video about the volcanoes on Earth, and I will not play it during this class, and you can watch it in your spare time. Okay. And earthquakes occurred in the subduction zones are quite different from the spreading center, because the largest and the deepest earthquakes occurred in such zones, and the shadow, not like the seismic event for the spreading center, only shallow or small earthquakes commonly occurred in the spreading center. And the location of most earthquakes define the top surface of a slab as it slides into the metal, and the surface to as deep as 670 kilometers. And quakes deeper than 100 kilometers are more likely associated with faults caused by stresses within the slab. And next, I will show the detailed information of collision zone of convergent margin. The continental crust is not recycled into the metal, and it is lighter and thicker than the oceanic crust. Yeah, as I talked before, the density of continental crust is is smaller than the density of oceanic crust. And when two fragments of continental lithosphere converge, the surface rock crumble together to form a collision zone. And the telescoping of the two plates and the buoyancy of the subducting continent eventually leads to a standstill of subduction within the collision zone. And the oceanic part of the subducting plate tears off and continues to drop down, a process referred to as a stab break-off. And continent collisions ultimately result in the formation of mountain ranges like the Himalayas or the Alps and some other mountain range. The collision zones that marks the closure of a former ocean from a spectacular mountain range. And the fourth type is a transformed fault margin. As I mentioned, and along a transformed fault margin, two plates grade past each other in a horizontal motion. It's a strike slip motion. Yeah, and this margin involves strike slip faults in the shallow lithosphere and often a broader shear zone deeper in the lithosphere. And most transform faults occur under water between oceanic plates. And transform faults occur as several different geometries. They can connect two segments of growing plate boundaries and one growing and one subducting plate boundary, or two subducting plate boundaries. And the North Anatolia Fault in Turkey and the San Andreas Fault in California are the two of the Earth's most notorious and dangerous transform faults in Earth. And notably that if you have interest on this, you can find a number of literatures or articles on the website of Sichuan University's library for the San Andreas Fault in California. And if you have an opportunity to attend American, to take part in the conference for AGU, like in San Francisco, maybe you can rent a car and drive there and see the fault which has an offset of the road. Yeah, it's very amazing fault you can observe the Earth. And the following are the two main features of the topography of the ocean floor. The middle ocean ridge I have introduced. Yeah, they have some. They extend on the Earth for approximately over 60,000 kilometers in length on the Earth, and the spreading centers. Also, another name of is the Divergent Margin. These separate plates, and the oceanic ridge with its central rift reaches sea level and forms volcanic islands. And the other one is the oceanic trench, which I have talked before. And as to the hotspots and absolute motion, although the vast majority of volcanoes on Earth are related to plate boundaries, like the mid-ocean ridges and the subduction zones, approximately 5% are classified as a hotspot. Hotspots are the product of the metal dipiers or plumes that rise through the metal as finger-shaped hot current and penetrate the crust. By the way, maybe there are a lot of strange terms or strange words for you. So yeah, later I will share a textbook about the plate tectonics with you in the group, so you can maybe you can read some part of it and know some of the very professional words or term to better understand the knowledge of this in this section. Okay, I will continue. And in spite of their the volcanoes, sorry, not the volcanoes. In spite of the plate boundaries, really have no numbers, and they play an important role in the convection system of the Earth's metal, and are responsible for about 5 to 10% of the melt and energy emitted by the Earth. And at the present, the current time, approximately 50 hotspots have been identified in both continents and oceans. You can see the figure, and although most of them are located in the interior of plates, and some hotspots are either coincident with mid-oceans ridges, like here, or in some close place. And Hawaii is a typical oceanic hotspot in Pacific Ocean. And during the 19th century, American geologist James Dwight Dunner observed that the age of the extinct volcanoes in the Hawaii island chain increases as one gets farther away from the active volcanoes on the Big Island. And the only active volcanoes are at the southeast end of the island chain, and the seamounts to the northwest are non-extinct. Earthquakes occur only near the active volcanoes for the Hawaii. At the main island of Hawaii, the nucleus of most recent volcanism in the Hawaii chain has been connected to the hotspot plume for less than 1 million years. And the resulting volcanic complex rises at the peak of Mauna Loa mountain to more than 4,000 meters above the sea level, and has its base at a water depth of more than 5 kilometers below sea level, and thus with therefore with nearly 10 kilometers of relief forms the tallest mountain on Earth measured from its base. Notice that it's the tallest mountain on Earth measured from its base, not from the sea level. You know the Everest mountain in Tibet is the tallest mountain measured from the sea level. Okay, and let's get back to the Hawaii. And the its diameter at the ocean floor is about 1,000 kilometers, roughly corresponding the diameter of the plume hit below. The island Hawaii will drift out of the sea of influence of the mantle plume within the nearby geological feature. And because the Pacific plate drifts over the plume at a rate of 100 kilometers is 1 million years, and approximately 30 kilometers southeast of Hawaii is a new volcano. Its name is Snowy High, and is currently under construction, and therefore the plume is not currently located directly beneath Hawaii, and the summit of Snowy High is presently at 1,000 meters below the sea level. And in the 1960s, Joseph Wilson proposed that a long-lived hotspot gneiss entered deep in the mantle beneath Hawaii, and a hot, buoyant plume of metal rock continually rises from the hotspot, partially melting to form magma at the bottom of the lithosphere, magma that feeds Hawaii's active volcanoes. And if the seafloor moves over the metal plume, an active volcano could remain over the magma source only for about a million years. And the island of, the island of Hawaii is currently in its mature stage of development, and but however, as the island moves off the nexus of the hotspot, the erosion process will take over and eventually reduce the island to a low-lying pile of volcanic rocks and debris. If we widen our scopic about the world hotspots, and there are several dozen hotspots that have been identified worldwide, and because the hotspot volcanoes do not form tracks on the Africa plates, so the geologists conclude that the plate must be very nearly stationary. And the hotspot transport roughly 10% of the total heat that escapes Earth. I mentioned the metal plume many times. What is it? The metal plume is an unveiling of abnormally hot rock within the Earth's mantle. As the heats of metal plumes can partly melt when they reach shallow depths, they are thought to be a cause of volcanic centers known as hotspots, and probably also to have caused flood basalts. And the metal plumes and the resulting hotspots are responsible for the formation of large volcanic complexes. These include volcanic chains up to several thousand kilometers long and huge flood extrusions, commonly called large igneous provinces or reef that consist of basalt lavas. And the metal plumes were probably more numerous 90 to 110 million years ago than today. And because the extinct seamount volcanoes of that age crowd together in the central Pacific. So what causes plate tectonics? In summary, they are following causes, and which are first, the mantle convection occurs in a variety of patterns, large scale and small scale. And then the hotter water is less viscous than cooler rock. It is critical to convection circulation. And hot, buoyant, low viscosity material rises in narrow columns that resemble hot spot plumes. And cooler, stiffer material from the surface sinks into the metal in sheets, which is similar to subduction snaps. And there are three forces which seem likely to have a part in moving the lithosphere. First of all, it is the ridge push, and which suggests that the young lithosphere site atop topographic high, and where gravity causes it to slide down the gentle slopes of the ridge. The second force is the snap pull at a subduction zone. As a cold density snap is free, at such a zone, it is free to sink into the metal. It pulls the rest of the lithosphere into the oceanic trench behind it. And the last one is the friction. The snap friction drags the top, the bottom, and the leading edge of the descending lithosphere in the subduction zone. And plate friction drags elsewhere at the base of the plate. These two factors in the friction could cause the plate tectonics. And this is a result of computer simulation of convection in an idealized Earth mantle. If you have interest, you can also find some papers about the computer simulation of convections from internet. And as far as I know, a famous professor whose name is Tang Chun'an Tang, Professor Chun'an Tang, who works in Dalian University of Technology. Actually, he's majoring in civil engineering, who is studied rock mechanics in the civil engineering. But recent years, he has very strong interest on the continental drift and the plate tectonics. He wants to be a geologist, so he has a very strong background of mechanics of rock. So he had done many computer simulations with his professional scenery about the numerical simulation about the continental convection about this. And if you have interest in this, you can very easily find his paper. And although the theory of plate tectonics has been widely accepted worldwide, but this theory does not explain why the plates exist. And at the present time, a number of scientific clues point to water as a missing ingredient in the plate tectonics. They argue that the water molecules can diffuse slowly through the solid rock, and water can weaken rock in several ways, and to explain this process. All this above is about the knowledge of continental drift and plate tectonics. And to be honest, this it is difficult to understand even for me. I'm not very professional on the plate tectonics, but I just know some the framework of it and the generalized scenery of it. So, but I think for you, some of you is difficult. But if you have a very very strong interest on this, yes, you can read some paper or textbook to better understand it.
Welcome to Earth, a restless planet with a violent soul. When the molten rock that hides beneath the surface reveals itself, it explodes, slithers, jerks, sloshes, and sometimes kills. It is the driver of continental collisions and cracks. Volcanoes erupt, mountains thrust skyward, and cities wait to die. All because of the liquid rock we call lava and its parent, magma. It is a creator, shaping our planet into what it is today. But it can also be a destroyer, responsible for some of our most frightening nightmares. So strap in as we take an adrenaline-fueled ride through our lava-driven world. Welcome to heaven, with a window into hell. This is the big island of Hawaii, home to Kilauea, one of the most active volcanoes on Earth, and perhaps the best place to see a planet's labor pains as it gives birth to itself. For some, this dangerous stuff oozing and spitting out of the volcano is the lifeblood pumped from the heart of a hot and vital Earth. But a better comparison might be a bad case of indigestion. This is a planet that belches, vomits, shudders, heaves, and passes gas. Really nasty gas. Whether from a pulsing heart or a heaving gut, lava is our only concrete glimpse into Earth's interior. Into an engine of creation and destruction that dwarfs all the powers of the planet's human inhabitants. Scientists study the sun, moon, and faraway stars. But in some ways, the center of Earth can seem more remote. So when clues to its inner workings appear on the surface, it's captivating. Follow this lava back down the tube into its home, and you're soon in the giant molten sphere that takes up the vast majority of Earth's volume, the mantle. Made of superheated rock so dense and hot that it moves like glowing taffy, the mantle churns in extreme slow motion. It's only about 2,000 miles down before you hit Earth's cores. But it may take millions of years for the molten round trip back up to the spewing spectacle that is Hawaii. To see just what lava can do, drain away the ocean and fly by the Hawaiian island chain, all children of volcanoes. Travel from east to west, and the islands grow progressively older. The youngest is Loihi. Although it occasionally spews lava, it might not break the surface for 200,000 years. Then there's Hawaii's Big Island with its 5 volcanoes, from seafloor to top, higher than the Himalayas. The further west you go, the smaller the islands get, sinking and eroding over time, each one a little older than the last. And all of them, like all land on Earth, born of lava. What's clear from the surface is that lava can create paradise. Within a year, on the scorched new Earth, vegetation takes hold. The volcanic surface is rich with nutrients, belched up from within. Eventually, sun, moisture, and microorganisms turn lava into soil, and life explodes. The gifts of the volcano have always lured humans onto its slopes. But what creates paradise can also bring disaster. In 2018, Kilauea began a months-long eruption, unleashing billions of gallons of lava that destroyed hundreds of homes and displaced thousands of people. Other eruptions have had a greater human toll. Mount St. Helens in America, Vesuvius and Etna in Italy, Unzen in Japan, Pinatubo in the Philippines. A litany of awe and terror. And the havoc hasn't just come from volcanic eruptions, but from those other terrible powers of the lava-driven world. Earthquakes, tsunamis, landslides, and a whole host of other deadly phenomena. Take a look at the places on the planet where volcanoes erupt and earthquakes shake. And suddenly, the world looks like something stitched together by Dr. Frankenstein. But these are not sutures. They're wounds in the world where the planet is ripping itself apart and bleeding out. And other places where it's smashing together and eating itself alive. It's at these seams that the vast majority of earthquakes rage and volcanoes explode. Why is Earth so restless? What causes the ground to shake violently? Volcanoes to erupt with deadly force? And mountain ranges to rise to incredible heights? The answer is plate tectonics. Lava is simply the visible part of what drives the action. The engine is the molten magma beneath the crust. Earth's surface is broken up into a dozen-plus chunks of different-sized plates, which skate around like planetary bumper cars. The plates float, despite their enormous mass, because there is denser material below. The continental parts of the plates are the lightest of all. They're granite-type stone, which may seem heavy to you and me, might as well be styrofoam compared to what lies beneath. A boiling pressure cooker of melted rock. Magma. Most of the boundaries between individual plates can't be seen because they're hidden beneath the oceans. Thanks to satellites and sonar, we know where and how impressive they are. Drain away the oceans, and we see a long mid-ocean ridge, where Earth is tearing itself apart and spitting up some of the highest mountains on the planet. Here, plates collide, move away, and slide past one another. And new crust is created as magma wells up to fill the void. Much of this underwater oozing takes the form of pillow lava. As the hot lava erupts on the cold ocean floor, a rounded bubble hardens quickly. As more lava pushes out from inside the flow, the pillow expands. New pillows burst through as the pressure increases. Equally spectacular are the smoking chimneys that are found along the ridge. Water that has seeped into the ocean floor is heated by hot magma and blown upwards. At the remarkable black smokers, water reaching temperatures in excess of 700 degrees Fahrenheit jets out. Their plumes can spread particles hundreds of miles away and release minerals that create chimneys up to 18 stories high. This geologic activity isn't confined to the ocean depths. There's one landscape where Earth is ripping itself apart, and you don't need a submersible to see it. This is Iceland, where a mid-ocean ridge managed to beach itself on land. Here, Earth stews in its own juices, much to the delight of humans, who welcome a dip into the geothermically heated spas that dot a forbidding landscape of black rock and blue-white ice. The cliffs here are the dividing line between the European and North American plates, and they're tearing away from each other at a rate of nearly an inch a year. This is one of the most geologically active places on Earth. Here, seemingly placid pools of water show signs of the violence that lies beneath the island. If you wait a moment, once the water starts to bulge, you better step back. And even under Iceland's glaciers, eruptions occur and wreak havoc. In 2010, ash clouds from Eyjafjallajökull volcano reached between 16 and 24,000 feet in the sky, disrupting flights for nearly a month and costing the European economy $5 billion. And it isn't the only sleeping giant lying in wait under the ice. The 6,500-foot-tall Bardabunda last erupted in 2014. And scientists predict that it won't be long before Iceland's largest volcano erupts again. Witnessing the chaos that occurs where Europe and North America meet, and looking east or west, you have to wonder, what's up at the plate's far edges? It stands to reason that if Earth's spreading here, it's got to be colliding somewhere else. And it is, sometimes fatally. Head about 5,500 miles east, and here's bustling Tokyo, smack above where the Eurasian plate hits the Pacific and Philippine sea plates. Let's try the other direction, about 4,000 miles west of Iceland. And here's the San Andreas Fault, where the North American plate hits the Pacific plate and runs just offshore of San Francisco. Tokyo, San Francisco. What do these two places have in common? In geological terms, they are cities waiting to die. So how did we get to this place where two of our most storied cities are on the endangered species list? To answer that, we have to go back to the beginning. Earth's dynamism was set into motion about 4.6 billion years ago, when on the edge of a spiral arm of one galaxy, a lot of space rubble starts circling in a slow gravitational dance. These rocks and gas are the remains of stars that exploded long ago. Eventually, this space junk begins to collect together under the force of gravity, lighting up from the energy of spectacular collisions. Planetoids smash into one another, causing some to shatter, others to merge. One planetoid will become Earth. It suffers constant cataclysmic bombardment and swells into a glowing molten ball. About 100 million years after Earth began to form, a change. Lava, the scum of the Earth at the time. This part of the molten magma sphere begins to cool and forms into a crust. For now, the crust will keep melting, but it's a start. Then something truly remarkable emerges. Lighter blobs of the molten Earth called cratons shoot to the surface and stick, giving rise to the beginnings of Earth's permanent crust. Meanwhile, the primordial Earth's interior has been belching out water vapor and other gases. Eventually, the atmosphere gets so saturated with water vapor that it begins to rain, in a continual downpour that drenches Earth for years. This leads Earth to take on its final form. A crust develops, thinner than a sheet of paper, with Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores. A liquid iron core, pulsing out a magnetic field that shields us from solar winds and cosmic radiation. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we don't know. Here's how it might have happened. At first, Earth had one giant supercontinent. Eventually, that landmass pulled apart and smashed back together, forming many supercontinents. After about 300 million years, the land masses separated and came back together once again in a new configuration, Pangaea. But then, Pangaea came apart. It's when Pangaea split that today's continents are thought to have formed. If you're confused, join the club. Even Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. So what forces are at work here? The rigid plates are driven by the slow movement of the super hot semi-solid mantle that lies below them. Like hot soup boiling in slow motion, superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call mantle convection. But what's the heat source that keeps this engine running? Some comes from decaying radioactive material, but most of it is left over from the energetic collisions and gravitational crushing that created Earth to begin with. It's still trapped down there, and it wants out. So what does this mean at the surface? Two things. First, magma being burped up along the ridges is pushing the plates in their respective continents apart, resulting in the rifts we see in Iceland. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the mantle. That's what we know, or what we think we know. The details of what's going on in the deepest parts of Earth that drive the engine of plate tectonics, we may never know. But what practically all scientists agree on today is that virtually everything on our planet is being shaped by plate tectonics, including the creation and destruction of life itself. There is one place on Earth where mountains stand as perhaps the greatest witness to the power of plate tectonics. These are the Himalayas, with Mount Everest their crowning glory. For those who attempt to climb it, it seems eternal, solid, and immobile. But looks can be deceiving. Everest and its Himalayan companions are slowly creeping upwards, even now. The Himalayas lay claim to 30 of the tallest mountains on Earth, and Everest, the highest of all, pokes a hole in the sky at 29,000 feet. On these mountains, higher than most humans would dare to go, you can find something fascinating: fossils from the depths of the sea. They are the remains of creatures from the trilobite family, some more than 500 million years old. How did they end up at the cruising altitude of an airliner? This dramatic episode of Earth's soap opera might be called When Continents Collide, and the result gives new meaning to the term upward mobility. It took place 175 million years ago, when something that looks suspiciously like India breaks off the southeastern tip of Africa and drifts north. Then, 50 million years ago, the leading edge of the Indian plate, which is oceanic crust, slams into the continental Eurasian plate. When the two continents meet head-on, the crust buckles upwards. The Eurasian plate crumples over the Indian plate. The collision of the two plates over millions of years has thrust the Himalayas and the Tibetan Plateau to their present dizzying heights. And they're still growing. Where they will stop, no one knows. GPS devices planted on the mountain show that Everest seems to be rising by an inch every 10 years. And that's how those little ocean-loving creatures got all the way up there. They used to live in the sea that India squeezed shut just before it rammed into Asia. But it's not just on land that these earthly collisions happen. Entirely different ones occur underwater. Sometimes, continental plates smash into ocean floor plates. Sometimes seafloor hits seafloor. And sometimes plates simply grind against each other, like ships passing too closely in the night. All to create topography as awesome as Mount Everest is tall. When the lighter continental plates crash into the heavier plates of the ocean floor plunges underneath, creating the very deepest parts of the oceans, its trenches. Let's drain the oceans once again and take a glimpse at the Pacific floor off South America. Here, the oceanic Nazca plate periodically rams into and surges under the continental part of the South American plate. In turn, the lighter South American plate crumples upwards, creating the towering Andes, the backbone of the continent. This makes them unstable and dangerous. Here, strong earthquakes rumble and killer volcanoes spew. In some places, ocean plate converges on ocean plate, and the result is a catastrophic downward dance that creates devastating earthquakes. The Mariana Trench, paralleling the Mariana Islands, for example, marks where the fast-moving Pacific plate converges against the slower-moving Philippine plate. One canyon, known as Challenger Deep, at the southern end of the Mariana Trench, plunges so deeply into Earth's crust that you could flip Mount Everest upside down and fit it easily inside. Here, too, volcanoes are born. Over millions of years, the erupted lava has formed volcanic rock on the ocean floor that piles up until a submarine volcano rises above sea level to form an island volcano. Such volcanoes are typically strung out in chains called island arcs. The intricate plate tectonics fringing the giant Pacific plate that results in this bounding and plunging and scraping form what geologists call the Ring of Fire. This massive 25,000-mile ring quakes and explodes up through Java, the Philippines, Japan, and Russia, rumbles east along the Aleutian Island chain to Alaska, then turns violently southward down the western coast of North, Central, and South America. Destructive earthquakes, volcanoes, and tsunamis all find a home in this Ring of Fire. So that leaves a compelling question. Where can a human go to find a nice, calm, geologically settled place to hunker down? Clearly not where Earth is tearing itself apart and creating volcanoes and earthquakes, or the places where Earth is smashing together, creating even worse volcanoes, earthquakes, tsunamis, and the like. Maybe we can retreat to the centers of the various plates and enjoy their quiet and tranquil beauty. The feel of solid, immobile rock beneath our feet, right? Wrong. Some of the scariest, most violent places on Earth lie smack in the middle of giant plates. There are many of these geologic hotspots around the world, but their impact could be more terrifying than anything humans have experienced before. So here we are, back in Hawaii, right in the middle of the giant Pacific Plate, thousands of miles from the Ring of Fire. At first glance, these isolated islands look like an ideal place to escape. But even here, danger exists. The physical evidence of the threat is lava, which tends to seep and spit lazily out of restrained volcanoes. It eats everything in its path, including what man has built, but usually moves no faster than walking speed. Only rarely have Hawaii's volcanoes lashed out explosively. What's Hawaii's secret? It's a plume of magma, a hotspot rising from deep within Earth's molten mantle that has somehow managed to break through the crust of the giant Pacific Plate. It has created in succession the islands of the Hawaiian chain until it reached here, under the Big Island and Loihi, the baby volcano that likely won't reach the surface for another 200,000 years. Because the Pacific Plate is moving northwest, but the hotspot itself stays put, each island is carried away as another one forms. The magma under Hawaii, rechristened lava once it emerges from its tube, is runny, almost liquid. It's been flowing out from under the Pacific Plate for millions of years. Layer upon layer of almost flat lava fields create rounded volcanoes that have been slowly building up from the seafloor. These volcanoes are called shield volcanoes for their gently curved shape. Despite their relative passivity, don't underestimate the tremendous power of these giants. Mauna Loa on the Big Island is more than 13,000 feet above sea level, which means it rises more than 29,000 feet above the ocean floor. This magnificent geologic feature would be taller than Everest if much of it weren't underwater. And what's above water makes up half of the Big Island. Although it's been quiet since 1984, it's an active volcano with 33 eruptions in the past 175 years. In contrast, its neighbor, Kilauea, has been disturbing the peace for more than 35 years. And in 2018, it became extremely violent. An explosion of activity was triggered when magma underneath Kilauea started to flow away from the deep crater chamber towards another part of the Big Island. This caused the walls of the summit crater to collapse. As the moving magma passed fissures in the ground, it erupted, spreading huge volumes of lava across the landscape. A lava channel seeping out of one of these cracks, Fissure 8, was so active it spawned a lava whirlwind. And it unleashed other threats. Once the 2100-degree lava hit the Pacific Ocean, it collided with seawater and created plumes of laze, a toxic mix of hydrochloric acid, steam, and tiny glass shards. Remarkably, in the first few months of this eruption, there were no human deaths. Why is that? Hawaii's volcanoes tend to have a slow and steady wins the race attitude that's reflected in their slow-moving lava, which comes in two forms, pahoehoe and a'a lava. Pahoehoe is a smooth or ropey lava flow, and it, along with a'a, splashes out of its volcanoes. A'a is a chunky, rough, broken lava flow. Over the years, the volcanoes of Hawaii have taken few lives. Only one in the last century. And possibly hundreds who happened to be in the wrong place at the wrong time back in the 1700s. Compare that toll to other volcanoes elsewhere. 36,000 killed by Krakatoa in Indonesia. The sound from its explosion was one of the loudest sounds humans ever heard. 30,000 killed by Palai in the Caribbean. Thousands more by Vesuvius and Etna in Italy. More recently, the death tolls have been lower, but the impact still significant. Nyiragongo, Republic of Congo, less than 100 dead, but 350,000 displaced as a river of lava covered 40% of the city of Goma. Mount Merapi, Indonesia, 379 deaths and 3.5 million affected when it spewed hot clouds of gas and ash over a densely populated area. Volcán de Fuego, Guatemala. Streams of lava and gas poured down its slopes, and ash spewed nearly 40 miles from the summit, killing more than 100 and affecting 1.7 million. Why is it that the volcanoes whose names reverberate through history lashed out instead of seethed? Why is this so terribly different from this? Or this? Or this? These look like real volcanoes, and they'll kill like real volcanoes. Welcome to the deadly splendor of the Composite Volcano, also known as a stratovolcano. Unlike Hawaii's shield volcanoes, which are flat and broad, composite volcanoes are tall, with steep sides, and they're violent. The steepness of their slopes hints strongly at their destructiveness. Famous composite volcanoes include Mount Fuji in Japan, Mount Cotopaxi in Ecuador, Mount Shasta and Lassen in California, Mount St. Helens and Mount Rainier in Washington, Mount Pinatubo in the Philippines. Some slumber, some smoke, and some wait. Why? Lava, apparently, has a very different personality from place to place. And in some locations, it's positively explosive. This is the lava from Mount Unzen in Japan. Notice how it doesn't run or flow or splash. It just hides under the rocks. And here's Montserrat. Its volcano just sits there. The lava's so thick it doesn't flow. Instead of sliding down the side of the volcano, it stays put. It grows spines, steams, and sometimes collapses. This lava doesn't melt. It's too sticky. It bulges out into a dome, the smoking silo of a natural bomb. When the lava-laden dome becomes too heavy, it can collapse, causing hot rocks, gases, and ash to explode out from the volcano. And what goes up must come down. The return of the flaming ash to Earth is called a pyroclastic flow, a burning avalanche that's hotter than your oven and moving at the speed of a bullet train. It's what stopped time for the Romans of Pompeii, entombed by burning ash in their attempts to escape. It's what swallowed a Japanese town after killing some of the most experienced volcanologists in the world. It's what left the capital of Montserrat in ruins. It's also what caused devastation around Indonesia's Mount Merapi and Guatemala's Volcán de Fuego. All around the world, stratovolcanoes like these are stockpiling their explosives, awaiting the moment when the magma below lights the lava fuse and detonates. Despite the destruction such volcanoes bring upon mankind, they are minor compared to the violence that the lava-driven world may have in store for us. On the day after Christmas in 2004, the world reeled at one of the worst natural disasters of our time, a huge tsunami. The cause of so much devastation? The most powerful kind of earthquake on the planet. A megathrust earthquake deep in the Indian Ocean. It killed almost 250,000 people. But if a megathrust occurs closer to the surface, the toll could be much greater. Megathrust earthquakes occur when one of Earth's plates subducts or plunges under the other. If the plunging plate gets stuck against the upper plate, the pressure builds until one plate suddenly and catastrophically releases, and a huge megathrust earthquake occurs. Widely thought to be the largest earthquakes the planet can generate, they often measure 9.0 or more on a Richter scale. And if one should occur on land, in a populated area, what then? Welcome back to Tokyo, home to more than 13 million people who live in a megathrust fault zone. About 140,000 died in the Great Tokyo Earthquake of 1923. In 2011, the world's fourth largest earthquake, measuring at a magnitude 9.0, struck off Japan's coast just 231 miles northeast of Tokyo. It triggered a tsunami with 130-foot-high waves and killed nearly 16,000 people. It also caused a meltdown at the Fukushima Daiichi nuclear power plant, displacing more than 100,000 people and releasing radioactive materials into the air and Pacific Ocean that drifted all the way to the United States. The fault could slip again. Magma is pushing the Philippine Sea Plate and the Pacific Plate under the Eurasian Plate, once thought to be 24 miles below the surface. We now know the fault between the plates is actually less than 3 miles down. That's why earthquake experts call Tokyo a city waiting to die. When the next big one hits, will Tokyo be leveled? Tokyo's geological nemesis could create a tsunami of immense proportions. But it turns out, it's not just earthquakes that can trigger a mega tsunami. Lying below the waves off the coast of Hawaii's Big Island, just out of sight, lie piles of rubble that extend miles out to sea. Apparently, that rubble didn't get there gradually. Instead, part of the giant Mauna Loa volcano may have collapsed catastrophically into the sea some 100,000 years ago, creating a mega tsunami that rebounded on the islands. Reaching a height of nearly 1/3 of a mile, the wave swept inland, tossing coral nearly 4,800 feet onto the great volcano's flanks. It would have dwarfed the tsunami of 2004. Off the sheer cliffs of Maui, even more rubble lies underneath the sea, evidence of an even bigger landslide. Apparently, these happen every 200,000 years or so. So, nothing to sweat about now. Perhaps. It's hard to imagine that Earth could have worse in store for us. But there's one place that may not lie quiet forever. Search the planet and you'll find no landscape quite like this one. Here, more geysers erupt than anywhere else on Earth. This is the world's first national park, Yellowstone. America's most popular tourist attraction is also a time bomb of unimaginable proportions. Something so devastating, it could possibly change the global climate for decades. The earliest geologists to visit Yellowstone understood that all of this beauty had uneasy geological underpinnings. But many speculated that because no volcanic peak or crater was visible, Yellowstone wasn't a threat. Then, field research in the 1960s and 70s proved them wrong. Pull out to a satellite view, and something awesome and frightening becomes clear. Much of the park sits on top of a volcanic crater, or caldera, roughly 30 miles wide, a supervolcano. It turns out that Yellowstone, like Hawaii, is a hotspot, with a plume of magma welling up from the mantle. Also like Hawaii, Yellowstone is always active on some level, and that activity results in magnificent sound and light shows. But unlike Hawaii, when Yellowstone blows, it will really blow. The land here rises and falls, up to 10 inches, pushed upwards by a swelling magma reservoir. Scientists predict that one day this bulging molten lava will burst through Earth's crust. It's just a question of when. Although it's been 630,000 years since its last powerful eruption, Yellowstone is very much alive and kicking. When the Steamboat Geyser had a string of eruptions after a 4-year silence in 2018, some began to worry. But scientists confirmed Yellowstone wasn't about to blow. The last eruption of a supervolcano was in Toba, Sumatra, 74,000 years ago. It was 5,000 times greater than Mount St. Helens, and its impact may have been felt worldwide. So much ash was hurled into the atmosphere that it obscured the sun. The ensuing darkness could have caused temperatures to plunge for years in some places. Sulfuric acid shot into the atmosphere and became acid rain that fell from Greenland to Antarctica. Scientists aren't sure whether man settled in the region just before the eruption, but there's evidence humans as far away as Africa took refuge along the coasts to survive the environmental chaos. Although the chance of an eruption of that scale is small, if Yellowstone were to go off today, what would the impact be on humanity? No one really knows. This is a dangerous planet we've found ourselves on, thanks to the magma machine that lies underneath us. But what may be disasters for us are entirely different things to Earth itself. The lava-driven world is similar to a living, breathing organism, full of stresses and strains, always seeking peace and equilibrium despite its internal conflicts. Volcanoes release internal heat. Earthquakes relieve stress on the surface. Life might have been born of lava, perhaps on some chemical wonderland created by smokers under a primordial sea. It almost certainly owes much of its diversity and hardiness to the plate tectonics that drives continents apart and smashes them back together again. Without lava, the world would be a cold, characterless stone in space. Instead, it blesses us with oceans and renews Earth's surface with rich, fertile land. It gives us a dynamic and animated planet, yet also holds our fate in its hands.
Okay, guys. I hope you get a stronger impression about the tectonics and its relationship with the earthquake and some topography evolution. Okay, so this is the knowledge about the plate tectonics and structural geology. And so next week we have a holiday in China, national holiday of China. So we don't have class next week, and we will continue our study on the next chapter, the hydrology, in 2 weeks later. Okay, guys.